let's see, last time we were studying integral domains, and we saw that every integral domain can be viewed as sitting inside a field. And this field right here, right, is called, I forgot to actually say this in the last lecture, so that field that contains the integral domain, it's called the integral domain's field of quotients. Right, so field, that was the name of that chapter that we were looking at, so I just want to, right, so the field that we constructed, that was D cross D star mod tilde, right, that is called the field of quotients of D. And now we're going to move on to a new chapter. So this is chapter 22, and it's about, we're going to study polynomials now, so polynomial rings. And polynomial ring, that's a major part of the study of rings, right? It's one of the motivating factors for why one would want to study rings. So we start off with a definition. So start with any ring. So let's let R be a ring. A polynomial with coefficients in R. It's exactly what you think, right? So, but we're going to be a little bit careful here. So this is a formal sum, which we'll write sometimes using, well, not too often, but occasionally it's useful to use sigma notation. Let's give it a name here, little f of x, equals sum, n equals 0 to infinity, a sub n. I think I want to use an I, don't I? Yeah, I want to use an I. I goes from 0 to infinity of a sub I x raised to the ith power, which is going to be a0 plus a1x plus a2x squared plus dot 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 going on forever, where each AI is an element of R, and what? And all but finitely many a sub I equals 0. Right, so at first glance, this looks like a power series. It's not, right? We write it, we allow it, sometimes it's convenient to think of it as going on forever so that we don't need to somehow stop at a particular degree. But we only allow finitely many of the a sub i's to be non-zero. So this does stop at some point, and after that, it's all zeros forever. Right? So it's not a power series. It really does stop with at some a sub n x raised to the n. So the a sub i's are the coefficients. Oh, and I should point out, what do I mean by formal sum? Well, in calculus, we think of polynomials as functions. And it will be convenient sometimes to think and use some function or some concepts from calculus and the theory of functions, right, in exploring polynomials. But at this point, we want to just think of it as an object, right? It is just a bunch of elements from R multiplied by powers of x, right? And that's it. If a sub I is non-zero for some I, then the largest I for which a sub I is non-zero is the degree of the polynomial f of x, right? So it's just the highest power. If they're all equal to 0, So if all a sub I equal to 0, then we say f of x is the 0 polynomial. And we define the degree, and define the degree to be minus infinity. Right, so there is a well-defined notion of degree for all polynomials then. It's either the largest power, right, the largest non-zero x, or a sub I, or the I corresponding to the non-zero a sub I, and then the 0 polynomial we define to have degree minus infinity. If the degree, and I'll abbreviate degree, so I'll just write deg of f of x. So if the degree of f of x is 0 or minus infinity, then f of x is a constant polynomial. Oh, and by the way, it seems a little strange that we're defining this seems kind of arbitrary. The 0 polynomial has degree minus infinity. We'll see why that's a convenient choice of degree a little later on. One thing to note, so let's say note that the set of constant polynomials corresponds exactly to R. We're going to define some operations. These are the obvious operations of addition and multiplication of polynomials that you learn when we're studying polynomials with coefficients in the real numbers. All right, so we're just going to generalize this. So if f of x is the polynomial sum I equals 0 to infinity a sub I x to the I, and g of x is the polynomial sum I equals 0 to infinity b sub I x sub I, we define polynomial addition, so f of x plus g of x is going to be the polynomial. So this will be sum I equals 0 to infinity. Let's write c sub I x sub I, where how do you add polynomials? You just add the corresponding coefficients. So c sub I is equal to a sub I plus b sub I. Add polynomials exactly as you think you should. And we're going to multiply polynomials in exactly the same way also, or the usual way. So we'll say and f of x times g of x is going to be a new polynomial, sum I equals 0 to infinity. Let's say d sub I x sub I, where, so now I need to tell you who the coefficients of this product is. So where d sub I is equal to the sum, I'm going to use a different symbol, I guess, J. Oh, no, d sub I, yeah, that's fine. Wait, what's... Oh, gotcha, okay. Where n, let's use it, n equals 0 to infinity, a sub I times b sub n minus I. Let's make sure I got that right. Oh yeah, it's I minus n. There we go. Now, this might look a little bit complicated. This is exactly what you do when you do a generalization of FOIL. When you multiply polynomials, you know exactly what you're supposed to do, and this is just the actual formula for multiplying polynomials as you normally would. One thing to be aware of: we did not require R to be commutative, so the order matters right here. So that's the one thing to be aware of. So note, if R is not commutative, then the order matters right there in the formula for multiplication. I mean, maybe I should be a little bit more, order matters in the formula for d sub I. Okay, so what's interesting about this set of polynomials, right? So far, it's just a set. If R is a ring, then the set R bracket X, and this set consists of all polynomials. Right, so this is of all polynomials with coefficients in R is a ring under the operations we just defined. So under the given operations. And this is the symbol that we use, R bracket X. That stands for the set of all possible polynomials. A few extra things here, so we'll say moreover, if R is commutative, then R bracket X is commutative also. If R has unity, then so does R bracket X also. If R has unity, then so does R bracket X. These are both fairly obvious. All right, but it's going to take some work to actually prove that we've got a ring here. So the first step, we want to show, and I'll use this ordered pair notation, that R bracket X comma plus is an abelian group. All right, so we're going to show that the set of polynomials is an abelian group under the usual addition. So let's take a couple of polynomials. Yeah, I mean, the distributive property is sort of obvious. Okay, but let's write it out. So let's let P of X equal sum A sub I x to the I, Q of X equal to sum, and I'm not even putting the subscripts, right? It should be I goes from 0 to infinity and so on, but we won't need those. Q of X is going to be the B sub I x to the I, and let's say R of X is the sum C sub I x sub I. Now we know that R is a ring, so addition is associative within R. All right, so since A sub I plus B sub I parentheses plus C sub I is equal to A sub I plus parentheses B sub I plus C sub I, we see that parentheses P of X plus Q of X plus R of X is equal to P of X plus Q of X plus R of X. So there's the associative property. for an identity, the zero polynomial is the identity. So the zero polynomial is the identity in R bracket X. For inverses, minus P of X is going to be the polynomial with where you just negate all the coefficients, right? And clearly, if you add this polynomial to P of X, you're going to get the zero polynomial. And then finally, the commutativity, right? So since A sub I plus B sub I is equal to B sub I plus A sub I, we have that P of X plus Q of X is equal to Q of X plus P of X. Okay, so that takes care of the additive property. We've got an abelian group with respect to plus. All right, we're trying to show that we've got a ring, so now we need to verify associativity of multiplication. And that's, you just got to grind it out. So the next step, multiplication is associative. Okay, so what do I want to do? Okay, so let's let d sub I, that's going to be A, should we call it A0? Yeah, A0 times B sub I plus A1B I minus 1 plus dot dot dot. Eventually we'll get to A sub I B sub 0. So this is the ith coefficient of our polynomial. So that would have been what, f of, or what did I call it? F or P? Oh, I called it P. Okay, yeah, P times Q. So P of X times Q of X. And then E sub I is going to be the ith coefficient of Q of X times R of X. So that would be B0 C sub I plus B1 C I minus 1. Remember, when you multiply these coefficients, they always add up to I. Right? That's sort of the rule when you multiply a coefficient. So this would be B sub I times C sub 0. So this is the ith coefficient of Q of X times P of X. P of X, Q of X times R of X. All right, so now the jth coefficient of P of X, Q of X times R of X is. So now I need to write this out, and it's you know, it's a little bit, well, first let's just say how it is. It's going to be D0 times C sub j plus D1 times C j minus 1 plus dot 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 plus D sub I C0. And then I want to write out who this is. So let's see, D0, yeah, D0 times C sub j is going to be A0 B0 times C sub j. Plus, okay, so now D1 times C sub j minus 1. I'm going to write that out as A0 B1 plus A1 B0 times C sub j minus 1. And you keep going. Finally, we're going to have di times C0, so that's going to be A0 bi plus a1 bi minus 1 plus dot 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 plus a sub I times b sub 0 times c sub 0. And I also want to look at the jth coefficient of what you get when you move the parentheses over. So the jth coefficient of p of x times q of x r of x is, all right, so that's going to be a0 times ej plus a1 ej minus 1 plus dot 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 plus oh, sorry, I put an I here. That should have been a J. Oh, shoot, did I screw that up? Yes, okay, sorry. That needs to be a J. And then these should be, these ones here need to be J's, right? So that should be a B sub J, 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 right? Because it was D sub J. Yep. Okay, and then this is going to be an AJE0. And then we're going to blow this one out also. So this one's going to be A0 times E sub J, which is B0 CJ plus B1 C sub J minus 1 plus dot 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 plus B sub J C0 plus, yeah, okay, so let's write the next one, plus A1 times B 0 C sub J minus 1 plus B1 C sub J minus 2 plus blah, 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 plus BJ minus 1 C0. Yep. Okay, and then you keep going until the last one, A sub J times E0, is just going to be A sub J times B0 C0. And now, supposedly these are equal. And so how do you see that? Well, you got to kind of, I don't know, turn your head sideways, I guess. So let's see. Where'd it go? C0. Well, I'm gonna yeah. What you need to do is show that there's a matching coefficient in every line. So let me see, for example, CJ minus 1, right? So this one right there, right? Oh yeah. Okay, so that piece right there, for example, is, let's see if I got that right. A0, B0, A1, B0, CJ minus 1. Yeah, all the way down. That's right. That's right. So that one right there matches that one. And then if you looked at the next portion right there, it would match that piece right there. So that's right. So you just kind of follow your way all the way out, and eventually you see, I guess I should have written that one a little bit shorter there. Right, you'll see a match. So it's kind of ugly, and I don't want to bore you with the details, but let's just say it like this. So using associativity, distributivity commutativity of plus. You can regroup one side to look exactly like the other side. We see that these are equal. So we see that these are equal. I don't know how illuminating this process is. I mean, it's just sort of grind it out, and you can check that the left side is equal to the right side. And so the coefficients match all the way down, which tells us that these two polynomials are equal. So therefore, P of x, Q of x, parentheses, times R of x is equal to P of x times Q of x, R of x. All right, the coefficients match exactly, and so we have equal polynomials. Yeah, okay, so now we just need to finish off the distributive property. So let's say now distributive laws. So let's do the ith coefficient. So the ith coefficient of P of x times Q of x plus R of x is, so that's going to be A0 times BI plus CI plus A1 times BI minus 1 plus CI minus 1 plus dot 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 plus eventually we'll get to what A sub I times B0 plus C0. And then if you multiply all this out, it's equal to A0 BI plus A1 BI minus 1 plus dot 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 plus, so I'm just doing the A's. Oh, that should be an A1 there, right? And then eventually you get to AI B0. And then do the same thing with the C. So I'm using distributivity inside R. So this is going to be A0 times CI plus A1 CI minus 1 plus dot 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 plus AI C0. And then what you're supposed to notice is that this is the ith coefficient of P of x, Q of x, and this is the ith coefficient of P of x times R of x. Since the coefficients match, we can then say that this polynomial is equal to this polynomial plus that polynomial. And that was left distributed property. The right distributed property follows similarly. So right distributed property follows similarly. To finish out the proof, right? So if R is commutative, then it's clear. So I'm just going to say check. All right, you can see this easily. So check if R is commutative, then right when you multiply, so just check P of x times Q of x is equal to Q of x times P of x. And if R has 1, right, the unity element, then the constant polynomial is unity in R bracket X. All right, so that completes the proof. I can't say it's the most exciting proof in the world. It's really just kind of grind it out to verify that we actually have a ring. But the study of rings is very exciting. So sorry, hopefully you bared with this. I know you got to watch it on film, which makes it even worse. But in the end, now we have a very important, exciting ring to study, right? So as we move on, it will get better, I promise. All right, that's enough for today. See ya.